Welcome to Ask and Learn.
In this problem, we have two discrete downward force vectors acting on a beam under which we have a linearly increasing response density force along the bottom, the opposite side of the beam pointing in the opposite direction. The distinct force vectors are 0.6 meters to the left, to the right of far left, and the second one is 30 kilonewtons, 0.3 meters from the far right. The entire span of the beam is 1.8 meters. Here, given this linearly distributed upward force, we are tasked with determining the values of W sub A and W sub B. These are force density values at the extreme ends of the upward force density relation. We're tasked with finding those such that this system would be in equilibrium with the combined force of the two downward force vectors. To solve this problem, we'll find the centroid of the two downward force vectors. We'll then write the upward force density as a function of x and parameters W sub A and W sub B. Third, we'll integrate to find the total load and total torque equations, and these will be in terms of W sub A and W sub B. Given both of those, we can then solve for these two unknowns, W sub A, W sub B. Each of these will have units of kilonewtons per meter. They are basically the y coordinates of a force density relation that spans the length of the beam. So for step one, we're finding the centroid and the total force from the two downward vectors. To find the total load, we simply add the two. 24 plus 30 is 54, and we have units of kilonewtons here. To find the centroid of the two downward vectors, we multiply each of their forces by their respective moment arms as measured by the extreme left of the beam. So we have 0.6 meters times 24 kilonewtons for the for the leftward vector torque. We have 1.5 meters times 30 kilonewtons for the rightward vector torque. We divide both of those. We divide the sum of those, in the numerator by the denominator 54 kilonewtons, which is the total force load magnitude. And we're left with 1.1 meters for the centroid of the beam from the downward forces. In step two, we're going to write a relation for the linearly varying density that of which points upward along the span of the beam. Looking at our diagram here, our final y coordinate is W sub B. Our initial y coordinate is W sub A, and we're going to divide that difference between the two, W sub B minus W sub A, by the length that's separating them. That is equal to the span of the beam, and it's 1.8 meters. That quantity is our slope, and for a linear relationship, we multiply by the slope the independent variable x, and that is the coordinate along the beam, And we need to find an offset as well. Our offset is the y coordinate when x equals 0. And for us, that is simply w sub a. So we now have our total, we have the force density written as a linear function here, as lowercase w's of x times the difference divided by 1.8, the difference between the two force density values at the extreme ends of the beam, plus the offset w sub a. In step 3, we're going to now derive equations for the total load and the centroid on the beam using the function we just derived, the linear function of the force density along that's pointing upward along the span of the beam. To find the force total, we take that function, multiply it by dx, infinitesimal dx, and integrate over the span of the beam. To find the centroid, in the numerator, now we're going to multiply by the product of the beam coordinate x times that force density function w of x times infinitesimal dx, integrating from over the span of the beam. And we're going to divide that evaluated interval by the total load. That will give us the centroid. Keep in mind that for our system to be in equilibrium, the centroid of the upward linearly varying force density must exactly oppose the centroid of the two downward forces. So we will end up plugging in our respective values that we calculated from the two downward forces, both their total load and centroid, and inserting them into the right-hand side of our equations for each, or I'm sorry, our left-hand side for each of these equations. So let's do the integrals for these two. First, for the total load, if we integrate this linear equation by over x, and again, that's the product of w of x dx, over the span of the beam, we're left with the slope times x squared over 2 plus w sub a, the offset, times x. And we're going to evaluate this definite integral from 0 to 1.8, inserting in our value from the two downward forces, our total load value from the two downward forces, which is 54 kilonewtons. After a little bit of algebra, not too bad, this can be simplified to the expression w sub a plus w sub b on the left-hand side over 54 divided by 0.9 kilonewtons. That gives us one equation we can use in our next step to solve for our two parameters w sub a and w sub b. The next equation we can derive by evaluating the expression for our centroid on the beam. This is a little bit more complicated integral. All we have to consider at this point is the numerator for our x total. I'm going to multiply our centroid value by the total load here, so we only have to worry about our numerator to evaluate. The slope from our linear function times x cubed now over 3 plus w sub a, the offset, times x squared over 2. This entire quantity, evaluated from 0 to 1.8, can be algebraically simplified to 1.8 squared over 6 times the quantity 2 times w sub b minus 2 times w sub a plus 3 times w sub a. And inserting in our centroid value and total load value from the two downward vectors, This equation can now be algebraically simplified as follows. 2 times W sub B plus W sub A equals our centroid from the two downward force vectors at 1.1 meters times 6 times our 1.8 squared. We had to divide by this coefficient here. That's why things are reciprocated here. And then our total load of 54 kilonewtons inserted for our total load. We now have a second equation containing both WA and W sub B and W sub A. Two equations and two unknowns. We can solve for the two unknowns, and here we do so. W sub A can be written as 60 minus W sub B. Inserting in this value of W sub A written in terms of W sub B into the other equation leaves us with 2 times W sub B plus 60 minus W sub B equals 110. That's what this evaluates to. And solving for W sub B here, we're left with 50.0 kilonewtons per meter. And again, that's for our final y-coordinate of our force density linear relation there. All the way back down. And now going back to this equation here, plugging in W sub B, we are left with 10.0 kilonewtons per meter. And that is our initial y-coordinate for our force density linear relation. That concludes our problem. Let me box these.